So maybe we can start. All right. So thank you very much, everybody, for coming. It's a pleasure for me to introduce today David Mateos. David started his career in the University of Barcelona several years ago. Then he moved on to some very prestigious postdocs from the University of Cambridge first, then to Perimeter Institute, and then to the University of California in Santa Barbara, before he got the position that he has now, the ICREA position. Okay, so David has worked on many different topics in theoretical physics, a wide range of topics, from early career topics on string theory, M theory, and now he's moved on to other things, also in fundamental physics, but today he's going to tell us more about things that have to do with observations, I hope. So we're going to hear about gravitational waves from the fifth dimension, and he will tell us exactly what that is. Okay.
Thank you very much, Jose Juan, for the introduction. It's really a great pleasure to be here with so many old friends. So in fact, I'm here to tell you a story which should be fascinating both for experimentalists and theorists alike. On the experimental side, we're going to be looking at two of the main discoveries in the 21st century, the quark-gluon plasma and gravitational waves. And on the theory side, we'll be talking about some of the most fundamental concepts in theoretical physics, such as the forces of nature, quantum mechanics, black holes, the number of space-time dimensions, etc. And all of this, which may look to you like a little bit of an eclectic list, is actually unified in a beautiful way if you think about it from the holographic point of view, which will require introducing a fifth dimension, as I will explain. By the way, if you have questions, don't hesitate to interrupt anytime. So of course, I have to do this in 1 hour or less, and that means that I'm not going to give you the details, but I will try to give you all the physical intuition that you need. And of course, there will be a few jumps and slight simplifications, but I will try to motivate and make everything plausible. And along the way, we will even perform a little experiment. Those of you who know me may be feeling a little nervous, but it'll be fine. So let me start with the forces of nature. You all know that there are 4 of them: gravity, the strong and the weak nuclear forces, and the electromagnetic force. And I'm going to start by talking about these 3, and we'll put in gravity a little later. The reason is that these 3 are unified with quantum mechanics. And this can be understood simply by looking at the physics of atoms, for the most part. So in an atom, you have electrons that are bound to the nucleus because of the electromagnetic interaction. And in fact, quantum mechanics explains why these electrons don't fall into the nucleus. But if you look more closely at the nucleus, you will see that it's composed of protons and neutrons. And in turn, if you look at those in more detail, you will see that they are composed of quarks and gluons. As far as we know, these are elementary. And these quarks and gluons are bound together inside these hadrons, these protons and neutrons, by the strong force. And in fact, the strong force is going to be one of the main characters in this story, because it's the only fundamental force for which we have a completely consistent quantum mechanical mathematical description. This theory is called quantum chromodynamics, QCD, but paradoxically, we don't know how to solve QCD. It's an extremely difficult problem that has been around for almost 50 years, in fact, more than 50 years. And we don't know how to solve it. If you have any ideas, please let me know, because we will get $1 million. Because one of the Millennium Prizes is to show that QCD, not even solving it, but just proving that QCD has a mass gap, which in practice is almost as solving the theory. So we don't know how to solve QCD, but we know a few things about QCD. The first one is that the strong force, which is described by QCD, is really strong. And that we know because these quarks and gluons, which constitute the proton and the neutron, etc., we don't see them as free quarks and gluons in nature, okay, at low energies. And that's because the strong force is so strong that they're always confined inside these hadrons. But we also know that any material in particular nuclear matter, like protons and neutrons, should melt at a sufficiently high temperature. So you could ask, at what temperature do quarks and gluons inside protons and neutrons get liberated because of thermal fluctuations? Okay? At what temperature does nuclear matter melt? So you may think that perhaps if you put it in an oven, that's enough, but that's not enough. Those of you who have tried to rob a bank may be thinking of a thermal lance. That reaches 4,000 degrees, so it can cut through steel, but it will not melt the protons and neutrons. Perhaps at the center of the sun, that's 15 million degrees, but that's also not enough. Actually, the temperature you need is 1 trillion degrees. So you may wonder, how on Earth or elsewhere are we going to achieve this temperature to melt these protons and neutrons? And in fact, the universe literally gives you an answer. Because if you go back in time in the universe becomes hotter and hotter as if you go back. And at some point, the temperature, around 1 microsecond after the Big Bang, was around this 1 trillion degrees at which quarks and gluons, before that time, were liberated. And at that temperature, you cross into another phase in which these quarks and gluons, because the temperature drops below 1 trillion degrees, they get bound into protons and neutrons, etc. Now, the amazing thing is that on Earth, we have actually succeeded in recreating a droplet, a little volume of this primordial quark-gluon plasma. It's called the quark-gluon plasma because it's composed of quarks and gluons. But before I explain the experiments with which we have accomplished this, let's do this little experiment. So I need you to all clap with me softly, okay, one time. So 1, 2, 3. Okay, now we have to clap a little harder. And now as hard as you can. Okay, are your hands warm? Yes? Okay, that's the kinetic energy being converted into heat. Okay, that's exactly what these experiments do. They take two big atoms, lead, gold, etc. They strip off the electrons, so they are left only with the nuclei. These are, each of them has about 200 nucleons. And then they collide them at speeds very close to the speed of light, at as high energy as possible. This was initially done in the US. Well, there's a long history, but the success history started in the 2000s in the US, as I will explain, at something called the Relativistic Heavy Ion Collider, and is now being done also at LHC at CERN. And what happens is the following. This is sort of an animation of what happens. So you have this huge kinetic energy. Part of it gets transformed into heat, and this heat is enough to raise the temperature of the resulting quarks and gluons, or initially the hadrons, above this deconfinement or liberation temperature. And what you get is, for a fraction of a second, a very small fraction of a second, a droplet of quark-gluon plasma. This lasts for about 10 to the minus 22 seconds, because this droplet is surrounded by vacuum, so it explodes. It has a huge pressure and energy density, it explodes, and as it explodes, it cools down, just like the universe. And when the temperature has dropped again below 1 trillion degrees, these quarks and gluons get bound together again into the hadrons that then detectors detect all over. And by looking at the result of this experiment, you can actually reconstruct the properties of this quark-gluon plasma. Are there any questions at this point? Please. Good. Good. So this has also, the reason to do this initially with ions is that what you're looking for here is to study the collective properties of these quarks and gluons. And for that, in other words, you want to create a new form of matter. So you want as much stuff as you can to really have collective properties. And in fact, for a very long time, there was a question about whether, if you did this with proton collisions, whether you would create enough of this to really be able to talk about collective properties. And the answer is, it turns out, it seems to be yes. And that's very surprising. I could elaborate on that, but this is the short answer. So this was, the discovery of this was the discovery of a new form of matter, okay, which exhibits collective properties, as I will explain. Good. So if there are no more questions, I'm gonna apparently switch gears and talk about black holes. And later you will see that this is intimately connected to the physics of black holes, perhaps surprisingly. So of course, you all know at some level, you have some idea of what a black hole is. Let me just say that it's some region of space-time which is causally disconnected from infinity because not even light can escape. So these are very mysterious objects, but we know many things about them, and the two things that you need to keep in mind today are the following. The first one is that when you have black holes orbiting around each other and eventually merging, you have a lot of mass going around, being accelerated, etc., and this produces gravitational waves, these ripples in space-time that propagate, and that were predicted by Einstein in more than 100 years ago. They were detected for the first time in 2015, 10 years ago, almost 10 years ago, and this merited the Nobel Prize in 2017. That's the first thing you have to remember. And the second one is that all the information about what went into forming the black hole, the technical term is, if you like, is the entropy of the black hole, is actually encoded not in the volume, but in the surface, in the area of the horizon, okay? This is an old result from a long time ago, but it turns out that this observation is actually much more general. It turns out that if you have certain theories of gravity, they are actually related. They can be described with degrees of freedom living at the boundary of the space-time. So let me explain this, because it is the concept of holography. So in a way, this result by Bekenstein and Hawking, if you like, is the first hint, or one of the first hints, into something called the holographic principle, which I will explain now. So the idea is that if you have some theory of gravity in some space-time, there should be an equivalent description of this theory in terms of degrees of freedom living at the boundary of the space-time. In the case of the black hole, you should think of the interior of the black hole as your volume and the area, the horizon, as this boundary. But this turns out to be much more general. This was suspected for a long time, but it wasn't until 1997, oversimplifying things a little bit, that we actually got a completely explicit example of what is this theory of gravity here and what is this theory in one dimension lower exactly. By now we have we have actually infinite families of examples of this. And it turns out, for the purpose of this talk, that this theory here turns out to be a theory of classical gravity. So it's some generalization of general relativity in 5 dimensions in an asymptotically anti-de Sitter space-time. If you don't know what it is, you don't need to know. It's just some very symmetric, negatively curved space-time. And that is supposed to be completely equivalent to some of the theory living at the boundary, which happens to be a copy of Minkowski space, which is very similar to QCD. So let me recap. Holography is the statement that some quantum field theory, this is very important, this is a quantum theory, similar to QCD, is completely equivalent in some regime to a classical theory of gravity in 1 dimension higher. Okay, it's important that this is classical in this limit and this is quantum. Now, if you believe this, then you can immediately ask the following question. I know that in this theory at the boundary, this is just some quantum field theory in flat space, let's say something like QCD, I can collide enough energy and form this deconfined phase, this quark-gluon plasma. What is the corresponding statement on this side? Because I told you that the two things are equivalent. And this means that any question you can ask here, you can also ask here, and vice versa. And the answer to that is precisely that the formation of this quark-gluon plasma corresponds to the formation of a black hole horizon over here. If you think about this, this is not completely surprising, because we know that black holes have thermodynamic properties. I just told you earlier that the area of the black hole gives you the entropy. So on this side, the area of the black hole will give you the entropy, the Hawking temperature will give you a temperature, and so on. All of these thermodynamic properties actually map to the thermodynamic properties of your thermal state. If you take your quark-gluon plasma, in equilibrium, if you could construct such a state, that would be dual to an equilibrium black hole sitting at the bottom of this space-time. But the real power of this duality or equivalence is when you go to a regime where you don't know how to describe this from first principles. Because after all, if you're looking at equilibrium states here, even for QCD, which we don't know how to solve in general, you can still take QCD and put it on a computer. This is called the lattice formulation of QCD. And you can compute equilibrium properties like the pressure or the energy density as a function of temperature, etc. But the moment that you ask dynamical questions, like what happens when you collide two nuclei, which is a time-dependent process, you form this core gluon plasma, it cools down again, etc. This is a regime which is quantum field theory out of equilibrium, which on this side, we don't know how to describe with any systematic method. Okay? In some limits, we can always do things, but there's no systematic approach for studying quantum field theory arbitrarily far away from equilibrium. It's in principle a perfectly well-defined problem, but it's a really, really difficult problem. But the point is that this now maps to a black hole that is no longer in equilibrium. It's a time-dependent situation, just like in here, but it's still a classical theory. So if you know how to evolve in time general relativity in 5 dimensions, which we know how to do numerically, just like we know how to simulate black hole mergers in 4 dimensions, if you know how to do that, you can translate this problem over here, solve it over here, and then translate back. That's the idea. So that's the strategy that we will follow. Are there any questions at this point? Okay. So let me go back to the quark gluon plasma. I just explained to you that we can use this side of the duality to learn about properties of the quantum field theory out of equilibrium that we may not know how to compute directly over here. So one of the questions that you can ask, and that was asked by experimentalists, as I will explain, was, well, if this is a new form of matter, properties, I explained to you that when you collide it, you form this droplet that then explodes. This explosion is controlled by fluid dynamics. And one of the key coefficients is the viscosity. Okay? The viscosity of this new form of matter contains a lot of information about the microscopic properties that you would like to understand. But it's impossible, in fact, to date, we don't know how to compute this viscosity from first principles using quantum field theory, using QCD. However, not for QCD, but for theories very similar to QCD for which we actually have this duality, this was computed using the gravitational side by these people in the early 2000s. And the interesting thing, because this is a theory of gravity, and you're trying to extract information about something that has to do with the boundary, is that the calculation that they did is essentially a calculation in which you perturb your black hole, you let it radiate gravitational waves in 5 dimensions, you read off what these gravitational waves are doing close to the boundary, and then from that you extract the viscosity of the quark gluon plasma. Okay? So this is the first appearance of gravitational waves here. This is in 5 dimensions, but I promise you we will get back to 4 dimensions. Now this was experimentally, you see this calculation was in 2001. This was experimentally measured at RIC around 2002, 2003. And they were extremely careful not to publish anything until they were absolutely sure. This goes to show that experimentalists are much more careful than theorists. And in fact, the result that they estimated was so close to 1/4 pi that this was the first time ever that in the press release of a big experiment, holography or string theory was mentioned. Okay? Because this was a big surprise. And in particular, this showed that holography can help you understand the dynamics of out of equilibrium quantum matter in terms of gravity in 1 higher dimension. And as I'm going to explain the rest of the talk, this has had and is still having far-reaching consequences. But before I get to that, scientific consequences, I want to discuss one sociological consequence that this had, which I think is interesting. So I have this friend who's a nuclear theorist, and she once told me that this result made this connection between nuclear physics and holography, made both fields respectable. Because she said, nuclear physicists, now they say, now we do deep stuff. Nothing to do with quarks and gluons and viscosities. What we do has to do, those mundane things. What we do has to do with black holes, extra dimensions, et cetera, all those cool concepts. Whereas the string theorists were saying, or the holographers were saying, now we do useful stuff. Nothing to do with black holes and extra dimensions and all those abstract concepts. Our work is really about quarks and gluons and viscosities and other measurable things, okay? There's a grain of, actually more than a grain of truth in this sort of joke. Okay, so let's go back to the scientific consequences. So the part that I have told you so far, the connection between the quark-gluon plasma and black holes, this is a story that's well known. What I'm going to tell you now is developing as we speak, okay? But it's a natural continuation of this set of ideas. Are there any questions? Perhaps about the sociology? Okay. So let me go back to cosmology. So I told you that if you go back in time, about 1 microsecond after the Big Bang, the temperature was precisely the right one to go from deconfined quarks and gluons to hadrons. But if you go a little further back, I think it's about a nanosecond after the Big Bang, the temperature was even higher. So at that time, what happened was that the electroweak transition took place. The electroweak transition is a transition where all the particles in the standard model acquire a mass because the Higgs field develops an expectation value. Okay? So it's sitting over here, and then it rolls down to the minimum, and this produces masses for all the particles. So you could ask, are either of these two transitions a first-order phase transition? Because if they were, so first-order phase transitions are basically what happens when you boil water. They take place through the nucleation of bubbles that grow and collide and so on, and replace one phase with the other. So this is sort of a violent process because the bubbles collide, they move matter around and so on. So if this had happened in the early universe, if either of these transitions were first order, this could have produced gravitational waves that potentially we could detect today or in the near future with different gravitational wave detectors. And this is really interesting because this could teach us about the early universe in a way that no other source could. However, it turns out that in the standard model of particle physics, strictly defined, both of these transitions are not first-order phase transitions. They are just crossovers. It means that the change from one phase to the other is continuous. Okay? There's no bubble nucleation or anything like that. So if you're a pessimist, this is really bad. But if you're an optimist, like me, this is great. Because this means that if we ever discover gravitational waves coming from a cosmological phase transition, this is the same as discovering physics beyond the standard model. So gravitational waves have the potential to teach us about things that not only are beyond the standard model physics, but in particular things that we may have no other window ever into. Because if the scale of the transition is sufficiently high, it's really unthinkable that we would ever be able to build an accelerator, a collider on Earth, to test such high energies. But the universe could do this for us. And these relics, these gravitational waves, could actually teach us about that. And in particular, one of the things that's really remarkable is that even though in the standard model strictly defined, these things are crossovers, we don't believe that the standard model is a complete theory. Okay? There are very good reasons to believe that it's not UV complete. So there has to be new physics at some scale above the standard model. And it turns out that even very minimal extensions of the standard model very easily tend to give rise to first-order phase transitions. This makes a lot of sense because the order of the transition, of course, depends on the details of the theory. So if you modify the standard model to extend it a little bit, it may happen that this becomes first order, okay? And not only that, but actually another remarkable coincidence is that if there is a first-order phase transition at a scale just above the electroweak scale, let's say 1 TeV, for example, then it turns out that the frequency of the gravitational waves that this phase transition in the early universe would have produced is precisely in the range to which LISA, which is this space interferometer that will be launched in the 2030s, would be most sensitive to. Of course, whether it will be sensitive enough to actually detect this signal, this depends on the details of the signal, and in particular on the strength. But the peak of the signal is determined basically by the temperature at which it took place. And if that temperature is around a TeV, then this peak would be in the sensitivity band of LISA. So for this reason, a lot of work over decades has actually been devoted to understanding what would be the signal coming from these phase transitions, the gravitational wave signal, if the phase transition is very similar to an electroweak phase transition. Okay? Because of the motivation of the fact that this could be seen with LISA. But since we don't know what lies beyond the standard model, it's really important to keep an open mind and remember that there could be phase transitions at temperatures very different from the electroweak scale. And the physics of these phase transitions could look very different from the electroweak phase transition. Okay? If we don't keep this open mind, we may miss discovery opportunities. And I will actually give you an example at the end of the talk of one of these situations in which the physics can be very different from an electroweak transition. Are there any questions? Yes, please. I'm going to come to this. Thank you. Yes. For the moment, the short answer is I'm looking at zero baryon density, and I will come back to non-zero baryon density. Okay, so I just told you that if there is a first order phase transition in the early universe, this will nucleate these bubbles that will grow and collide, and these dynamics will produce gravitational waves. And it turns out that, of course, the gravitational wave spectrum that you produce is sensitive to some properties of the phase transition, like the latent heat, the temperature at which you transition, etc., etc. But the one that it is most sensitive to is the velocity with which these bubbles expand once they've been nucleated. Not only is this one of the most important parameters, but it's actually the hardest one to compute. In fact, it's so hard that even in weakly coupled quantum field theories, we don't know how to compute this from first principles. And the reason for this is that unlike the latent heat, which is an equilibrium property that you can determine if you know the equation of state, this velocity is an out of equilibrium property, because when the bubbles expand, they push the plasma in front of them out of equilibrium, and then you need to solve a dynamical problem in order to determine this. Okay? And this in quantum field theory, to date, we don't know how to do. But we can do this in theories for which we have this dual 5-dimensional classical gravitational description available. So the strategy in those cases is extremely simple. The problem that you would like to solve in your quantum field theory is the problem in which you have a metastable phase and you have nucleated a bubble of the stable phase. Because it's the stable phase, it has higher pressure than the metastable plasma outside, so it will expand. And what you want to do is to determine this terminal velocity once it reaches a steady state. Since we don't know how to do this, we translate this to a problem in gravitational physics in 5 dimensions. And that means that you have to start with initial conditions in which, far away from the bubble, your horizon corresponds to the metastable phase, and near the origin, your horizon is deformed in such a way that this corresponds to the stable phase. Okay? And then you simply solve or evolve in time Einstein's equations in 5 dimensions here with these initial conditions, and you translate the result back to the gauge, to the quantum field theory at the boundary. Is this strategy clear? So what I'm going to show you is the result of doing this. Okay? If you solve the dynamics here and you translate back, what I'm plotting for you here is the energy density in this theory as a function of position, and when I click the button as a function of time. And what you get is this. The inside is the stable phase, is the bubble of the stable phase. This region here is the bubble wall. And you see that as it expands, it pushes the plasma in front of it. It heats it up. By energy conservation, what you take out from the inside has to go outside. So it heats it up and it pushes it out of the way. Okay? So let me insist, this is the result of evolving in time Einstein's equations in 5 dimensions and translating back to the language on this side. So simply by repeating this calculation for different nucleation temperatures, you can determine, for example, the velocity as a function of nucleation temperature, which is something that people studying gravitational wave signatures are very interested in. Good. Any questions? Please. Forget about those. Those are an artifact. This is I've been asking my collaborators to update the movie. This is an artifact of the way we prepare initial conditions. I can go into that, but it has absolutely no physics in it. So please completely disregard it. Any other questions? Okay. So now I'm going to come back to your question about the baryon number or baryon chemical potential. So everything I've told you so far about these bubbles is in the cosmological context. Okay? And in cosmology, the only thing you care about essentially is energy and momentum and temperature, because there's no other conserved number, or there's no other net charge. Okay? But now let me go back to QCD. If you remember, I told you that in QCD, it's been well established that if you heat up quarks and hadrons, protons and neutrons, if you heat them up, when you go to quark-gluon plasma, this transition here is a continuous transition. It's a crossover. It's not a first-order phase transition. However, in certain situations, like for example in mergers of neutron stars, what is merging is an object that is extremely rich in baryons. Okay, there's a net proton of protons and neutrons in a neutron star, and not antiprotons and antineutrons. Okay, so what that means is that there's a net chemical potential for baryons, baryonic chemical potential, or a net quark density, if you want. So one of the open problems that has been open for decades in nuclear physics is to determine what is the phase diagram of QCD as a function of temperature and baryon number. And in fact, it's been conjectured, and it is strongly believed, that this crossover actually, as when you go up in chemical potential, becomes a line of first-order phase transitions. And this point here would be a second-order phase transition. That's called a critical point. And the reason this is believed to be the case, but has not been established, is that a lot of effective models for QCD, but not QCD itself, because we don't know how to solve it, but we know how to build effective models. Almost all of these effective models predict this line of first-order phase transitions. Of course, they disagree about the exact location of the line and the exact location of the critical point. That's model dependent. But the conclusion that there should be, that this should turn into a first-order phase transition, seems to be fairly robust. But we don't know how to establish this from first principles because we don't know how to solve QCD. Even less at non-zero baryon chemical potential. And like I said, this is a problem that has been open for decades, and it's been attacked both from a theory point of view and experimentally in heavy ion collisions, but there's no conclusive answer yet. And what I want to show you today is that actually these neutron star mergers, and in particular gravitational waves coming from these neutron star mergers, could actually settle this. So just to emphasize again, this is a first-order phase transition between hadronic matter and quark matter. This quark matter is another form of deconfined quarks and gluons. But you see, if you go this way, the quarks and gluons get liberated because the thermal fluctuations are so strong that they break apart the protons and neutrons. If you go this way, they get liberated because you're compressing protons and neutrons so much that at some point it becomes indistinguishable to what proton or neutron a given quark belongs. Okay? So it's a deconfined form of quark matter. Okay, so why am I saying that neutron star mergers could actually settle this? The reason is the following. People simulating mergers of neutron stars, what they actually simulate is general relativity in 4 dimensions, coupled to hydrodynamics. The hydrodynamics is what describes the dynamics of these protons and neutrons, or quarks and gluons, etc., as a fluid with a given equation of state. So if you could compute the equation of state for QCD on the lattice, and you give it to these people doing these simulations, they will predict for you what the merger will do and what the gravitational wave that will get produced will be. So these people have actually done simulations in which, of course, they don't know exactly what equation of state they should take, but they have taken an equation of state of this type, qualitatively speaking. So an equation of state that has a crossover here and a line of first order phase transitions here, just to see what are the possible consequences of having this first order phase transition here. And what they see is really interesting. They assume that initially both neutron stars are pure. So all the way down to the core of the star, you only have protons and neutrons, no quark matter. But then when they collide, because of the violence of the collision, parts of the star get heated up and other parts of the star get compressed. So that means that some fluid cells in the stars go this way or go this way. So you're pushing them into the quark matter phase, okay? Simply because of the dynamics of the process. And this is what you see here. These are snapshots of the post-merger system, and these contour lines correspond to regions where the temperature and the chemical potential, which they can track because they are really evolving these variables, actually fall on this side. Okay, so this is evidence that in the merger, you actually do cross this line of first order phase transitions if it's there. Of course, that's what we don't know. But if it's there, you're very likely to cross it. So then you can ask, well, what happens exactly dynamically when part of your fluid, which is actually a few kilometers in size, gets pushed into the quark matter phase? Well, what happens is that you took some hadronic phase, you heat it up or you compress it, so initially it becomes metastable. And once you've compressed it enough or heated up enough, you will then start nucleating bubbles of the preferred phase. So this is sort of the inverse process of in cosmology. In cosmology, the universe is cooling down, and you nucleate bubbles of the low energy phase if you have a first order phase transition. Here, you're nucleating bubbles of the high energy phase because you're compressing or heating up the system. So it's superheating versus supercooling. I hope this is clear. So these quark matter bubbles then will grow, they will collide, and this dynamics produces gravitational waves. And the key point to note here is that the frequency, the characteristic frequency of these gravitational waves is set by the one scale that is relevant at the time of production, which is the typical bubble separation when they collide, or the typical bubble size. And this is easy to estimate based on QCD scales, etc. And it turns out to be about 0.5 kilometer. So just to put this into context, remember that a neutron star is between 10 and 12 kilometers in size. So when you collide two of them, you get 20 kilometers. These regions where you nucleate these bubbles are about a few kilometers in size. And if you count how many bubbles you actually nucleate, you get this 0.5 kilometer characteristic size. And if you translate that into frequency, that's almost a megahertz. Okay? This is a much, much higher frequency than the usual frequency that you get in the merger, in the primary signal, which is kilohertz. Okay? Kilohertz is what LIGO and Virgo saw when they detected for the first time in 2017 the gravitational waves coming from a neutron star merger. Okay, there's an in-spiral phase, but when they merge, it's about a few kilohertz. This is 3 orders of magnitude higher. Okay, so today we don't have any detectors capable of detecting this frequency. This is too high. But there's a strong experimental effort to try to detect this with lots of different types of technologies. Just to mention one of them that I'm familiar with and that people in Barcelona are involved in, you could try to detect this with superconducting resonant cavities. So the idea is that there's some gravitational wave, there's some magnetic field here, the interaction between the gravitational wave and the magnetic field gives you an electric field. So you charge the cavity and then you measure the electric field, and through that you detect the gravitational wave. So the reason why this megahertz signal is really interesting is that, first of all, this is the only astrophysical signal in this frequency range. In fact, the only astrophysical signal above the kilohertz that only relies on standard model physics. I only used QCD here. There's nothing beyond the standard model. And this is a very important fact for experimentalists because they want to have a clear motivation of things to look for. And the second thing is that this gives you direct experimental access to the QCD phase transition, because these bubbles will not appear if the transition between hadrons and quark matter is a crossover. Okay? Only when it's a first order phase transition you nucleate bubbles. Any questions? Okay, so then I'll move into the final part. So I'm going to go back to cosmology. And I promised you that I was going to show you an example in which a cosmological first order phase transition could be very different from an electroweak phase transition. Okay, so this is what I want to tell you now. So the standard picture that people have developed over 30 years of how this cosmological phase transition could take place is the following. First of all, you assume that the transition is very fast because it happens on a microscopic scale compared to the expansion rate of the universe. Okay? This is almost always a very good approximation. And for that reason, you ignore, as a first approximation, the expansion of the universe, the Hubble expansion, and you imagine that you're nucleating these bubbles and they are expanding and colliding in flat space. Okay? This is a good approximation as long as the time that it takes for this to happen is short compared to the characteristic expansion rate of the universe. Okay? So in this approximation, the picture that people have in mind is that these bubbles will get nucleated, they will collide, expand and collide, and then they will leave behind, they will disappear and leave behind the stable phase in a homogeneous state with little perturbations on top of it, sound waves. And just to show you this is a simulation by these authors in which you see these bubbles being nucleated, they expand, they push the fluid around, of course. These different colors that you see here are these sound waves propagating back and forth. But you see that all the bubbles eventually merge. The interfaces between the bubbles, which are the walls, disappear. And at late times, what you have is the stable phase with, this is the last one, with perturbations on top of it that, of course, live for a very long time, these sound waves. They get attenuated, but very slowly. And this is what actually produces most of the gravitational wave signal, the fact that these waves live for a Hubble time, roughly speaking, okay? A cosmological time. Okay, so if you think about this, you may wonder, how is it possible that I go from my initial metastable phase to the final homogeneous state with little perturbations on top of it? What is happening to energy conservation? Because remember, we are in the approximation in which we are ignoring the Hubble expansion. If you ignore, that's what this simulation is. If you ignore the Hubble expansion, in your box where you're simulating this, the total energy is conserved. Okay? Your equations conserve the total energy. The only thing that would not conserve it is the dilution due to Hubble expansion. But that is not being included here. So the reason why this is possible is because if you go to the phase diagram of these electroweak-like theories and you plot energy density as a function of temperature, you get this familiar multi-valued plot where the critical temperature is here. So let me explain this. This part, this upper branch, is the globally preferred state at high temperatures, okay? This one here is metastable. It's still locally thermodynamically stable, but the preferred state at these temperatures is actually in this branch here, okay? So this is stable, this is metastable, this one here would also be metastable, and the one in between is unstable. It's called the spinodal region, okay? So in this case, what is remarkable is that suppose that the universe comes down this way, it crosses Tc, and at some point, when the bubble nucleation probability becomes large enough, you start nucleating. Let's say it's here, okay? Then once you start nucleating here, your energy is over here. Whatever you end up with has to have the same total energy at the end of the process, because I told you if you ignore Hubble expansion, energy is conserved. But in this case, there's an available candidate here on the stable branch, which indeed has the same total energy. So it is possible for this type of phase diagram to go here, nucleate, and at the very end up here, because it's available and it has the same energy. Is this idea clear? Okay. But this is puzzling because actually this type of phase diagram is not completely generic. you could ask, what happens? Imagine that the phase transition is, instead of being electroweak-like, imagine it were QCD-like. Okay, QCD is not a weakly coupled theory. And in fact, the phase diagram in QCD is very difficult to determine, in particular this region here. But it has actually been determined, I would say, with a fair amount of confidence in recent years. And it looks like this. And you see, the remarkable thing now is that in this metastable region now, there's no other state with that same energy that is homogeneous. In fact, there's no other state, stable or not, that is homogeneous with that energy density. So if you nucleate when the universe has this energy density here, the only place the universe can end up at is a phase-separated state. Let me explain this. So if you take a bathtub and you fill it up with water, okay, but you arrange for the energy density, the total energy, to be in between the energy of water and the energy of ice, you will end up with a mixed phase in which you will have some ice cubes floating in water. Okay? That's an available state with the correct energy density, but it does not have, but it's not homogeneous. Okay? So what I'm telling you is that if in the early universe there was a phase transition in a theory that has a phase diagram like this, then the final state cannot be a homogeneous state. It has to be a phase-separated state. And to show you this, here's another simulation now with a phase diagram with this one that I'm talking about. And what you will, so in this case, we only nucleate 2 bubbles for clarity. You can do it with any number of bubbles. And now what you will see is that the bubbles will indeed merge, but they will settle down. They will not disappear. Okay? So they slow down, they merge. And then they will reach a steady, actually a static configuration at late times. There it is. So at this final state, what you have is that even though you nucleate it here, okay, below Tc, the bubbles expand, they heat up the plasma outside, and they heat it up back to Tc. So what you have outside is again the phase at Tc, and inside you have the low energy phase again at Tc. Because Tc, the critical temperature, is the only temperature at which the pressure here and here is the same. So it's the only temperature at which you can have phase coexistence. Okay? And this is necessarily the final state of the cosmological first order phase transition if you ignore the Hubble expansion. Okay, so this is my last slide. So the conclusion of this is that the standard picture of the way that a cosmological first order phase transition takes place is strongly dependent on the qualitative properties of the phase diagram. If you have a phase transition like the one I showed you, which is generic for strongly coupled theories, then that transition cannot complete if you ignore the expansion of the universe, because the final state then, because you conserve energy, will be a phase-separated state. And for that reason, the characteristic time and length scales in the transition are going to be different, because they have to be bigger than Hubble, than if you have an electroweak. So in fact, this idea that the phase transition could proceed through this phase-separated state, intermediate state, this goes back to Witten, at least in 1984. But as far as I know, nobody has done a detailed calculation of the gravitational wave spectrum in that case. But you're completely correct that, as you saw, the dynamics slows down a lot. And slowing down means that the frequencies are going to be lower. I don't know how low. This is not a calculation we have done yet, but that's a really good question. Yeah.
Any other?
So, as far as I understand, it seems to me that this works only in one way. So we know how to do the calculations in the gravitational theory, and then we predict some qualitative properties. So can we expect the other way around? Can we expect some predictions from QCD that we can use in GR?
Absolutely. In fact, the way that I've been using the duality is the easy way, in the sense that you use classical physics to understand quantum field theory. But you're completely correct that actually the biggest promise of this duality is that it's giving you a UV complete definition of quantum gravity. So because we know how to do in principle quantum field theory in Minkowski space, the idea is that this quantum, even though, so let me go back. For the purpose of this talk, I told you, let me go back to this picture here, maybe here. Here. So I told you that for the purpose of this talk, this is a theory of classical gravity, and this is some quantum field theory, but the real duality, so this is true in some limit, but the real duality is an equivalence between some quantum field theory in flat space and some theory of quantum gravity in asymptotically anti de Sitter space. So in principle, all the questions that you may want to answer about quantum gravity, all the puzzling, information paradox, topology change, all of this is encoded in this quantum field theory. So I think your question is in the direction of, well, can I then use this to understand all the things I want to understand over here? The answer in principle is yes, but of course in practice, it's very complicated, okay? And I think progress has been made, but it's still an ongoing research program. But yes, the answer to your question is yes, you can do that.
So in the QCD phase diagram, you said that we have this line that is initially a crossover, then a first order phase transition. And you said that there is a point in which we should expect a second order phase transition.
Yes.
What should we expect if we just hit that point by chance?
Actually, this is something that is a very active program of research. So in these heavy ion collisions that I described, what happens is the following. Here. So if you do these heavy ion collisions at very, 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 very high energies, what happens is that so you form this droplet, and even though this droplet has a little bit of a net charge or a net quark charge, quark density, because the energy that you're depositing, the kinetic energy, is so high, the ratio between the net charge, or if you want the chemical potential and the temperature, is really, really tiny. So you're basically exploring this region. Okay? But then at RIC, they have actually concluded something called the RIC energy scan, where what they did was to start at very high energies and start lowering the energy in the collision. The idea being that then you would be exploring this region, then this region, then this region, then this region. And their goal was to actually identify the existence, experimentally, of this critical point. Why? Because the critical point, being controlled by a second order phase transition, has a lot of interesting properties. For example, the dynamics of the plasma slows down here. The speed of sound of your perturbations in the plasma goes to 0 at this point. Okay, so they were actually trying to see in the data, also another result that happens there is that fluctuations get enhanced. If you know this experiment where you put a liquid and you bring it to a critical point in pressure and temperature, and you have this critical opalescence, that's exactly thermal fluctuations being enhanced in distance because of the critical point. So they were trying to see in the data an enhancement of fluctuations due to the fact that when the droplet expands and cools down, it would be coming down from high temperature to low temperature, and it would come very close to the critical point. As far as I know, the results from the latest run are not yet published. The ones that were published were inconclusive. Okay, they were not. There was like a 2 or 3 sigma evidence, but not enough to claim discovery. And I don't know what the situation is because the latest results have not been published, and they should be published anytime. So experimentally, they built an accelerator to look for this. That's billions and billions of dollars. And so far, it's inconclusive. That's why I was saying that this has been, we have tried to establish this from a theoretical point of view and from an experimental point of view, and so far there's no conclusion.
Any other question? Actually, I have one. In this case, where you have the bubbles that at the end is stop, at some point, this must conclude. I mean, you cannot have just bubbles in the universe today of the old phase. So what's the story? How does it end?
You mean when you go through phase separation?
Yes.
Yeah, so what will happen is that the universe, so that's what happens if you ignore Hubble expansion. If you now put back in Hubble expansion, that will dilute the energy density everywhere, both inside and outside. And in fact,
the pressure will change.
exactly. So the idea that people have in mind of what's going to happen is that when you go to phase separation, you go here. But now Hubble expansion will dilute it. So this point will move again, will cool down a little bit, and this one will cool down a little bit. And that means that the pressures will no longer be equal. The pressure here will be slightly bigger than that. So these bubbles that initially had settled down will begin to grow again. But this dynamics now is much lower, because now this is driven by Hubble expansion, not by a difference in pressures. This has, in Minkowski space, this would not happen. So this very slow dynamics, the idea that people have in mind is that it will simply be adiabatic, and the bubbles will very slowly grow, merge, and then fill up the entire space, and that will be it. I think it may be a bit more complicated than that.
Okay.
But I don't think this is completely, nobody has simulated this, for example.
Okay. Okay, so there's been lots of questions, but is there any other burning question? If not, let's thank David again.